what I've come to understand over the years is that the education and instruction related to statistics has been fairly, oh, I don't know if there's a nice way to say dumbed down, except to say streamlined for people who don't have much of a math background. All right. So what they want to do is they want people who aren't really math proficient to also be able to part in statistical analyses. And the natural drawback to that is, you know, it's kind of like buying really, really expensive cutlery, like chef quality cutlery, you know, like the restaurant grade for somebody who doesn't know how to cook, you know? So it's wasted on that kind of population, but it's not wasted on us because we have a math background. You know, you had to, because you had to take a bunch of classes in order to get here, right? So, and those classes, even if you didn't do so hot in them, you at least did well enough to understand the things that we're going to go over in this class. All right, so we're going to talk about the, for lack of a better term, the origin of the standard deviation. All right, so a little bit of a background. So we know that it's a standardized score. It's a value that, and we've talked about this a couple of times, that we know it's a value that's comparative in nature. It's designed to take information from one data set and use it to translate to other data sets. And in fact, if I, you know, in the next lesson, when we learn about z-scores, we'll learn how I could take a score from one set of data and transform it into a score for another set of data. So for example, you know, I could, off the top of my head, inflation kind of jumps out as a reasonable comparison. But I would say, for example, a good example would be like, let's say you got a 90 in an algebra class, right? And you know that historically class averages in algebra classes typically end up being, let's say, 70 with a standard deviation of 5. All right, so it's completely made up, but for the sake of this this analogy, I'm going with that. So standard deviation 5, the mean of 70. It's historic values. Data were collected or was collected over long periods of time, and that's what it turned out to be. Maybe nationwide, maybe worldwide, maybe universe-wide, right? Because math is transcendent. So you have that information about algebra, and you want to know, okay, how's that gonna translate into my success in geometry the next year? So then you know that historically the class average in the geometry course is a 75 with a standard deviation of 2, right? So what you can do is you can take the score, standardize it that you get in algebra, yeah, and assume that not much is going to change in terms of your approach to the class, and translate it into what the score would be in that geometry class the following year, right? And get a sense. You know, there's variables, you know, lurking variables. I mean, if you got a different teacher who does things completely differently than any way that teachers in the past have ever done, like they flip it up on you. This year would be a good example of that. This is completely like, it's not my idea to flip it up on you, but it's flipped up on you. You know, this is not how the course is typically taught, right? We would already be like 5 group activities in already, you know, so it's different. But that's an example of the power of standard deviation, being able to translate from one group to another. Now, it still doesn't really talk about the meaning of a standard deviation. All right, so I'm gonna throw a simple expression or a phrase at you, and we're gonna say the average deviation. So I'm using a term in its own definition. So that's like terrible. That's like the #1 thing not to do, right? But for some reason, when you look in online sources, textbooks, you hear teachers say it, they'll say the same thing, average deviation from the mean, right? So it's like, okay, cool. And then there's a question of whether they even understand the concept, right? So that's a different story altogether. But I'm going to take that word deviation and I'm going to replace it with one of two words, depending on which one you prefer. Displacement or distance. Now, the key word in the whole thing, you know, you don't get hung up on one word. It's the sneaky one here is the average deviation from the mean. It seems like we're using the same word twice in the same phrase, you know, like average of the average. Yeah, that's exactly what it is. Because what we're going to do is we're going to find the displacement from the mean, and then we're going to average all of those displacements. All right, so I think the best way to understand this is using a graphical approach. That's where my brain takes me. Some people just like memorizing definitions, and that's wonderful for some folks. You can do what you need to do by memorizing. Oh man, this is going to sound rude. Memorizing the words of others. That's really what it is, right? But there's more to it than that, because some people are really good at memorizing concepts. You know, they got the definition down, they memorize the definition, but through it all, they know what the concept really means. They just they don't bog themselves down with always going back to basics. They say sometimes it's just better to know that secant squared plus 1 is equal to 10, right? Or I'm sorry, tangent squared plus 1 is equal to secant squared. Jeez, I always get that backwards. So anyway, this is an ordinary XY axis or XY coordinate system. Now I'm going to say that we have a raw set of data, and I'll just kind of chuck it off on the side. It's not going to be an overly lengthy set of data, so that's why I can chuck it off on the side. All right, so that data set has X values that I'm going to call X sub I, just to keep it organized. Because we're going to work in general terms here. We're going to have, I'm not going to give you particular numbers. I'm going to say we have one X value, another X value, another X value, and another X value, and then, you know, as many X values as we need. So I'm going to say we have X sub 1, X sub 2, X sub 3, X sub 4, X sub 5, as many as it takes in order to get to X sub whatever the last one is, X sub n. All right. Now this is single variable data, right? So, oh, apologies, folks, in the classroom. Let me get rid of some of this stuff. I mean, you can probably tell based on what I was saying, what I was writing, and in most cases, you know, it's going to be available to you anyhow. So, but if something's in the way and you can't see it, just throw up a paw and let me know. Right? So we have X1, X2, X3, all the way to Xn. Right? Now, I could also look at these as ordered pairs, right? Because these are really X values. All right. So I'm going to change my X along the X axis to an X sub I. Right. So it's a really important distinction. It's an X sub I in order to correspond with my X values. But the big question would be, well, what about the Y's? Well, there's only one variable. All right. So I could designate Y as whatever I want, right? In order to keep things clean, what I'm going to do is I'm just going to say that Y is equal to 1 for all of these X values, all right? So if I want to, you know, I could just I can scoot this over a little bit. And make a Y column where they're all 1. So I'm sort of making it a frequency, or having it have a look of a frequency table where every X value has a corresponding value of 1 because they only occur once, right? And so what do you get when you have an X value followed by a Y value? You get an ordered pair. All right, so I'm going to plot those ordered pairs. I want to keep my leg crossed, but I also want to move close enough to be able to manipulate this. So, whoa, there we go. Now I'm going to crush the computer under the weight of my leg. So, ordered pair, meh. Ordered pair, additional meh. More meh. Lots of mehs. All right, all of those are ordered pairs. So I'm going to plot one here. A little benchmark for one. Now, the issue that I run into here is I don't know whether X of 1, X of 2, X of 3, whatever, I don't know if they're positive or negative. So that's kind of a big issue. So what I do is I just place them wherever I want, knowing in my mind that some of them are going to be positive and some are going to be negative. Now, what I can do is I can make an assumption, a reasonable assumption, I think, that if I have a data set and I want to keep it organized, odds are I'm going to put the list of X values in increasing order, right? So if I have some negative values, it's going to be for the lower values of X. So like X of 1, X of 2, X of 3, and so on. So I can make that assumption. So what I'll do is I'll just throw a point over here, X of 1. I'll do that in black for consistency. Color coding purposes, as it were. X of 1, Y sub 1. I'll throw another one here, X sub 2, Y sub 2. I have Y sub 2, geez, holy moly. Good TV show. Not what I was thinking of though. X sub 3, maybe we'll assume that that's a positive value. It could also be 0. You put it right on the axis if you want. So maybe I'll do that. But then you're kind of pinning it down as a value of 0. So I want to have the freedom to establish it as anything, some kind of positive number. So maybe I won't. Maybe I'll just put it over here. And then, we'll have a bunch of other points, all these points, whatever, eventually culminating. So I'll just do ... culminating somewhere with an X sub n. All right. So those are the points graphically. And the Y value could have been whatever I wanted. All right, I could have left it at 0. And like just conceptually, I could say, well, there's no 0, there's no frequency. So I'll just put it on the x-axis. It's just a matter of it's on the same horizontal. That's all that really it amounts to. All right. Now, we're also going to have the mean. All right. The mean we note using an X bar. That's nothing new. All right. So that X bar, I could put wherever I want. Let me do that in green, yeah. I put that wherever I want, all right? Because again, this is a floating set of data. I don't know the values, so I don't know where the mean would be. I guess the only thing that I have to keep in mind is that the mean is a measure of center. So it should be somewhat centrally located. All right, so what I'll do is I'll just kind of chuck it over here. Call that X bar. All right. So what I'm going to do, and this is the part that can be a little dicey because everything else is just a visual representation of stuff we already know. I'm going to get rid of the bottom half there. What I'm going to do is I'm going to connect each point with the mean in the appropriate order. All right. So I'm going to find this line segment. And what I'm going to do is I'm just going to snag that out. And we're going to find the distance, all right, or the displacement. So this is the coordinate x1, 1. And then that mean, I plotted it on the same level as all the other points. So yeah, it's X bar, but it's also comma 1, because that's on the same level if I'm plotting it. So X bar, comma 1. All right. So then, so that was the first point, and I'll reconnect it later. I'm just doing this for organizational purposes. So the second line segment, we need to find that value, that displacement, X2, 1, X bar 1. And you see why I didn't choose too many of these, because it would have gotten a little crazy. See if I can sneak that. Oh, come on. There we go. Tuck it down here. Little tiny segment. X3, 1. And X bar 1. And then, you know, using a little common sense and an idea of the trend, you can figure out what the last one is, but I'll throw it in there anyway. I mean, there's many more because we also have the dot, dot, dot. So I'll even put that. Dot, dot, dot. X sub n, comma 1. X bar, comma 1. All right, so these are all the distances the mean is away from the given, the individual given values. All right, so I can, like I said, I can just reconnect. I was going to copy paste, but I think it's actually easier to just draw them in. So I have this one. That was the last one. I had the black one. I had the red one, and then the green one. Oh, overshot the map. All right, so all those distances. You know, it's hard to see. That's why I kind of pulled it all out. All right. So in terms of computation, there really isn't much going on here because I need to find displacement. Now, if you remember your displacement formula, also known as the distance formula, depending on the course that you learned it in, you actually learned it in, if you took both of these courses, physics and any form of math over the last 3 or 4 years, you've learned both terms. It's just you might be more comfortable with it if you took physics because you used it a lot more. All right. So displacement distance. Now it's distance traveled. Traveled have 2 L's. Feels like it does. Feels like what I wrote was wrong. So we have our displacement formula or distance formula, x2 minus x1 squared plus y2 minus y1 squared, all the way back to algebra 1. Okay, maybe even before that, based off of the Pythagorean theorem. So it's nothing, nothing really new there. All right. So if you apply that to each one of these cases, then you'll see you just need to apply it to one before you realize, okay, I know what the relationship is going to be. You'd have, for example, d is equal to, and the reverse is true, by the way, so x1 minus x2. So we have 2 possible ways of representing this. We could say x bar minus x1 plus y, sorry, 1 minus 1 squared. We could also say x1 minus x bar squared plus, so the reverse order, 1 minus 1 squared. All right, so this all amounts to the same thing. It simplifies down. You know, this will zero out the 1 minus 1. The x minus x bar squared under the radical, they both would eventually simplify down to the same thing. You'd have x minus x1 minus x bar squared under the radical, which is x1 minus x bar. All right, so that's what your displacement is. But really, if you're just finding the distance between 2 points on a number line, distance formula, displacement formula isn't necessary. If I tell you that on a number line, you have a point plotted at 5 and another point plotted at 13, how are you going to find the distance between the two of them? You're going to subtract. All right, so it makes sense that this would play out this way. So this one would be x sub 1 minus x bar, but it does all come from that displacement concept. All right, x2 minus x bar, x3 minus x bar, and x sub n minus x bar. All right, so that's the deviation. What we want to do is standardize that deviation because some of them are going to be positive and some are going to be negative. All right, so the next idea that came into play was, okay, I need to find the average of these values. All right, so I have these possibly very large quantity of values all the way up to whatever the nth value is. I need to average all of those. All right, so if I'm gonna average them all up, what do? I take the sum and then divide. But if the displacement, if the distance between them is equal to 0, that's fine. But if it's negative, then that might balance out some positive. So what we do before averaging the values, we square them to remove negatives. And the question that always would come up would be what I was mentioning like a week ago, I guess. Why not just take the absolute value? And that the answer to that was normal distributions, because if you do it one way, it doesn't tie together with some of the stuff that comes further down the line in statistics. So you run into that negative, not negative, but like the con, you know, the drawback to the approach. And so what we do is when we're taking the average, normally I would say, okay, I got my x bar 1 minus x, I'm sorry, x1 minus x bar plus x2 minus x bar plus x3 minus x bar all the way up to x sub n minus x bar. And we would normally divide that by n. And let me just do a little correction here. That should be the dot, 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 plus here, plus there. All right, and it would normally be divided by n. All right, but again, we have that little issue of, yeah, but if we do that, we're gonna counteract some of these values. Some of them are gonna be negative, some of them are gonna be positive, and we don't wanna deal with that, so let's square them all first. All right, so this is really, the squaring part is just an add-on step to the concept of taking the average value of the deviation. So the average deviation within the data set, it's an add-on to guarantee that all values are positive, right? So square them all. But then when we're adding up a ton of values, we don't really want to do it this way, because if we do it this way, what we end up with is an issue. If there's 100 values, I'd have to write a really long numerator. So instead of doing it that way, I would say, all right, well, I'm going to take the sum of all the x of I values. So the x of I minus x bar squared value. So all of those entries within the numerator spanning from I equals 1 to the nth value. All right, going from the first to the last. And then we'll take that and divide it by n. Instead of writing that whole thing over n, what we do instead is we just write 1n. And then what we end up with here is known as the population variance. All right, that population variance is it's useful, but we're not quite there yet. Right? We need the sample variance, and the short explanation for that at this point is just we're going to divide by -1 as a correction technique. There's more to it than that, but and it has to do with limits, and it's a conversation that I can't have just yet, because I know that there's some students in this class that are taking pre-calc this year, so they haven't gotten the limits yet. So I got to sit tight on that, but it's coming. All right. So the other variation of this formula, which is for the sample variance, just involves an n-1. But again, more detail on that coming down the line. All right. And just taking the square root of these values will give you the standard deviation. All right. So if I'm looking at this is my S equals, this is my sigma equals, I'm sorry, sigma squared, S squared. And we know that S is equal to the square root of S squared. All right. And so that's really the origin story behind these formulas, where they came from. The whole page of fun. Look at all that. Very colorful. So I'll make this available, obviously, because that's been the MO for the whole course. But this should help a little bit. And honestly, for the conclusion parts of your work, of your submissions, anytime you're talking about standard deviation, because standard deviation is not a one-off. It's not a concept that we're going to just talk about this week, next week, whatever, and then be done with it. We're going to be talking about it for the whole year. All right. So it's always coming back. So the sooner you get a solid understanding of what it's really telling us, the better off you're going to be. So you have this mathematical derivation, which is wonderful. I'm very proud of what I see on paper here. It just looks really nice. But honestly, I'm proud of it more because of the color. It just looks very vibrant for a Friday morning. But it's that first line that tells you everything you need to know. It's the average, well, the first two lines, average displacement or distance from the mean. All right. So if you can wrap your heads around that idea, then I think you got it. All right. So I'm going to end it there. Stop the recording.